Welcome to Late Night History. Tonight, you do not have to go anywhere. You can stay exactly where you are, settled into the dark, with the weight of the day finally setting itself down somewhere just out of reach. And while you rest, I want to take you on a journey downward, not outward into the stars, the way these slow night stories so often go, but inward, down through the floor beneath you, down through the soil and the bedrock and the layers of stone that have been pressing on each other since long before anyone was here to name them. Down to a place no human eye has ever seen and no human hand will ever touch. Down to the very center of the world, where there is something waiting that is so strange, so quiet, and so vast that when you truly understand it, it does not frighten you at all. It only fills you with a kind of slow and spreading wonder, the sort that loosens the shoulders and lengthens the breath. So let me begin with the strangest thing of all, the thing that sits right at the heart of everything we are going to talk about tonight. At the very center of the earth, there is a ball of iron. And it is enormous. If you could somehow lift it out and set it down in space beside the planets and the moons, it would be roughly the size of Pluto. The inner core, as it is called, has a radius of about 1,220 kilometers. Pluto, that distant pale world out at the cold edge of the solar system, has a radius of about 1,188 kilometers. So the iron sphere buried beneath your feet is, very slightly, a little larger than Pluto, a whole dwarf planet of solid metal hidden inside the one we live on, turning quietly in the dark, and almost no one ever thinks about it. Sit with that for a moment, because it is worth sitting with. There is an entire world's worth of iron down there, a sphere 2,440 kilometers across, and it has been there far longer than any mountain range you could name, far longer than any ocean in its present shape, far longer than any living thing. And it is hot, not warm, not merely glowing. It is hot the way the surface of a star is hot. The visible surface of the sun, the part we see as that unbearable disk of light, the part scientists call the photosphere, sits at a temperature of roughly 5,500 degrees Celsius. The iron ball at the center of the Earth is estimated to be somewhere between 5,200 and 5,400 degrees Celsius, and by some estimates it may run hotter still, which means that if you could stand somehow at the boundary of that inner sphere, you would be standing beside something as hot as the face of the sun. The same searing furnace temperature that pours light across 93 million miles of empty space to warm your skin on a summer afternoon is sitting right now, this very moment, beneath the chair you are sitting in, beneath the bed you are lying on, beneath the foundations of every city that has ever stood. And here is the part that should not make sense. Here is the small, impossible thing that the rest of tonight's story will gently unfold for you. That iron, hotter than the surface of the sun, is not liquid. It is not a churning, glowing, molten sea. It is solid. A solid ball of iron, frozen hard as the densest stone, even though it is hot enough to vaporize almost anything you could lower toward it. How can that be? How can something be that hot and still be frozen solid? It is the first real question of the night, and it is a beautiful one. And the answer is so simple and so strange that once you understand it, you will never picture the center of the Earth the same way again. The answer is pressure. We are used to thinking about heat as the thing that melts. We hold a candle flame to ice, and it turns to water. We pour heat into a pot, and the butter goes soft and runs. Heat melts in our everyday world. But there is a second character in this story, one we almost never notice because in our ordinary lives it rarely gets a chance to flex its full strength. That character is pressure. And down at the center of the Earth, pressure rules everything. The weight of the entire planet is pressing in on that inner core from every direction at once. Every kilometre of rock, every layer of mantle, every drop of the molten metal ocean that surrounds it, all of it bears down toward the centre, squeezing inward with a force almost impossible to imagine. The pressure at Earth's centre is somewhere around 330 to 360 gigapascals. Now, a gigapascal is a unit that means very little to most of us, so let me give it to you another way. That pressure is more than 3 million times the pressure of the air around you right now. 3 million times. The gentle, invisible weight of the atmosphere that you never even feel, the air that fills your lungs and rests on your shoulders without you ever noticing it, multiply that by 3 million, and you begin to approach what the iron at the center of the world endures every single second of every single day. And here is the lovely mechanism, the thing that resolves the paradox. When you squeeze a material that hard, you change the rules, you change the temperature at which it can melt. Iron, under the crushing pressure at Earth's center, simply cannot turn to liquid at 5,400 degrees because the pressure pushes its melting point up and up, far higher than the temperature that is actually there. Think of it this way. Imagine a crowd of people packed so tightly into a room that no one can move their arms, no one can even shift their feet, everyone pressed shoulder to shoulder and back to chest, locked in place by the sheer number of bodies. You could shout at them, you could turn up the heat, you could fill that room with energy, and still no one could break free to dance because there is simply nowhere to go. That is what pressure does to the iron atoms at the center of the Earth. They have the energy to move, the heat to move, the temperature to move, but they have nowhere to go, so they hold their places, they lock into a solid crystal, atom against atom, even at a temperature that would, anywhere near the surface, turn iron into a glowing river. So this is the first wonder of the night, and I want you to carry it down with you into your rest. At the center of the world there is a ball of iron the size of a dwarf planet, hotter than the surface of the sun, and it is held frozen solid not by cold, but by the unimaginable weight of everything above it. The deepest, most extreme place in all the Earth is also, in its way, one of the stillest. A vast hot heart, locked into stillness by pressure, turning slowly in the dark. Now you may have heard something about that turning. You may have caught a headline somewhere in the rush of an ordinary day that sounded alarming. Perhaps it said that the Earth's core had stopped. Perhaps it said the core had reversed. Perhaps it carried that breathless edge of warning, the kind that makes you wonder for half a second whether something is wrong with the ground beneath us, whether some catastrophe is quietly brewing far below. I want to take that worry from you tonight, gently, and set it aside because the truth is so much calmer and so much more beautiful than the headline ever was. And once you understand what really happened, the words changed direction will stop sounding like a threat and start sounding like something closer to breathing. A slow, deep, patient rhythm, far older than us, far larger than us, that asks nothing of us at all except, perhaps, that we marvel at it for a moment before we drift off. Here is what actually happened, told slowly the way it deserves. That iron ball at the center of the Earth does not sit in dry stone. It is nested inside something extraordinary. Surrounding the solid inner core is the outer core, a vast ocean of liquid iron and nickel, more than 2,000 kilometers thick, a churning, flowing sea of molten metal. The solid inner core floats within that liquid ocean, suspended in the middle of the planet, free, in a sense, and to turn. And because it is surrounded by liquid rather than locked into the solid rock above, the inner core does not have to spin at exactly the same rate as the rest of the world. It can drift, it can creep a little faster, or lag a little slower than the mantle and the crust that carry us through our days and nights. For a long time, scientists came to believe that the inner core was creeping ahead, that it was spinning just slightly faster than the rest of the planet, gaining the tiniest fraction of a turn over the surface above it, year after year after year. They called this super-rotation. The iron heart racing forward by a hair, leading the planet in a slow private dance of its own. And then, in the year 2023, two scientists at Peking University, Yi Yang and Xiaodong Song, published a study that gently rewrote the picture. Looking at decades of evidence, they found that this small lead, this faint forward creep of the inner core, had been slowing down. Year by year, the inner core's race ahead had been easing until, around the year 2009, it reached a point of near balance. For a moment, in the long history of the planet, the inner core and the mantle above it were turning at almost exactly the same rate, in step, neither one ahead. And after that turning point, the inner core may have begun to drift the other way. Not racing ahead anymore, but lagging slightly behind, drifting, ever so gently, backward, relative to the ground above. Now hold on to this next part, because it is the whole heart of the matter, and it is what turns alarm into peace. The inner core did not stop. It did not stop turning, not for a moment, not in any way that you or I would recognize as stopping. It is still spinning right now with the rest of the Earth, once around every 24 hours, exactly as it has for ages, exactly as it will tomorrow. When we say the inner core slowed, when we say it may have reversed direction, we do not mean it froze in absolute space and hung motionless in the dark. We mean something far more delicate. We mean its tiny lead over the mantle slowed and stalled and may have tipped into a tiny lag. It is the difference between two runners on a track, both running the same direction, both moving forward, but one of them slowly drifting from just ahead of the other to just behind. Neither one ever stops, neither one ever turns around and sprints the wrong way. One simply, gradually, gently loses a step and falls a little behind. That is what happened far beneath your feet. The iron heart did not halt and did not reverse against the heavens. It changed by a fraction of a degree its relationship to the ground we stand on. And it did so over decades, so slowly that no one felt a thing, so gently that the only way we even noticed was by listening very, very carefully to the planet itself. Yang and Song suggested something even lovelier about it. They proposed that this slowing and turning back is not a one-time event at all, but part of a rhythm. A slow oscillation, a back and forth, with a cycle of roughly 70 years. Which means the inner core may swing gently forward for decades and then gently back for decades, like the slowest pendulum in all the world, like a tide measured not in hours but in human lifetimes. If that is true, then this thing that the headlines called a catastrophe is in fact one of the most serene processes imaginable. A vast iron sphere the size of a dwarf planet rocking back and forth in its ocean of molten metal across the span of a human life. The way a cradle rocks, the way a chest rises and falls in sleep. There may have been many such turnings long before any of us were born, quiet reversals that no one noticed because no one was listening, each one a slow breath of the planet, taken over the course of 70 patient years. So if you came here with any worry that the ground might be failing beneath you, let it go now. Let it sink down out of your shoulders and out of your chest. Nothing is wrong. Nothing is breaking. The Earth's heart is doing what it has very likely done countless times across the ages, turning a little forward, then a little back, in a rhythm so slow it makes the seasons look hurried. There is nothing to brace against tonight. There is only something to wonder at. And before we go deeper, I want to do a small thing, the kind of thing we do on these quiet nights. I would love to know where in the world you are listening from. Whether you are in a city wrapped in winter or somewhere warm with the window cracked open to the night air, or far out in the countryside where the dark is truly dark and the only sound is the wind. If you feel like sharing, the comments are there, and I do read them. And there is something gentle about knowing that all of us, scattered across the whole turning surface of this planet, are resting tonight above the same slow iron heart. And if you are new here, and you find that this kind of slow journey helps you settle towards sleep, you are welcome to stay. There are more stories here of the same unhurried kind, waiting for whenever you want them. But for now, you do not have to do anything at all. You only have to listen and let the descent carry you down, because there is a question hanging over everything I have told you so far, and it is perhaps the most extraordinary question of the entire night. It is the question that turns all of this from a collection of strange facts into a genuine mystery, the kind that wraps around your mind and pulls you gently into it. How can we possibly know any of this? Think about it for a moment. I have just told you the size of the inner core down to the kilometre. I have told you its temperature, hotter than the surface of the sun. I have told you the pressure that holds it solid. I have told you that it slowed its rotation around the year 2009 and may now be drifting backward relative to the mantle in a 70-year rhythm. And yet no human being has ever seen the inner core. No instrument has ever been lowered to touch it. No camera has ever sent back an image. No probe has ever sampled a single atom of that iron. No one has ever been there. And here is the truly humbling part. No one ever will. Not you, not me, not anyone who comes after us for as far into the future as we can sensibly imagine. To understand just how unreachable it is, consider the deepest hole that human beings have ever managed to dig. It is called the Kola Superdeep Borehole, drilled in the far north of what was then the Soviet Union, a project that ground its way downward for years and years with enormous effort and enormous machinery. And when they finally stopped, when they reached the absolute limit of what was possible, the deepest they had managed to go was about 12.26 kilometers, just over 12 kilometers into the Earth. It was and remains the deepest hole humanity has ever made, a genuine triumph of stubbornness and engineering. Now hold that number up against the distance to the center. From the surface of the Earth down to the very center is about 6,371 kilometers. So that deepest hole, the deepest scratch we have ever managed to make in the skin of our own planet, after all that labor, reached down only about 12 kilometers out of more than 6,000. That is roughly 0.2% of the way to the center. 0.2%. If the journey from the surface to the inner core were the length of a long walk across an entire country, our deepest borehole would not even take us to the end of the driveway. We have barely broken the surface. We have not even truly begun. The mantle, the outer core, the inner core, within it, all of it lies thousands of kilometers beyond anywhere a human tool has ever reached, and beyond anywhere a human tool ever could reach, because the heat and the pressure that hold that iron solid would crush and melt and erase any machine we could ever build long before it got close. And yet we know the iron ball is there. We know its size and its heat and its slow, strange turning. We know it changed direction around the year 2009. We know all of it with real confidence about a place we can never visit, a place sealed away beneath thousands of kilometers of stone and molten metal, a place as far beyond our reach as the bottom of the deepest sea is beyond a creature that has never left the shore. So how do you come to know in such detail the shape and the temperature and the very rotation of a thing you cannot see, cannot touch, and will never reach? This is the master mystery of tonight's journey, the thread we will follow slowly down into the dark. And the answer, when it comes, is one of the most beautiful things in all of science. We did not dig our way to the inner core. We did not bore down to it or send anything toward it. We learned to listen. We learned to hear the inside of our own planet the way a doctor hears the inside of a chest, the way you might hear which room of a house someone is moving through just by the sound of their footsteps carrying through the walls. We learned to read the echoes of earthquakes ringing through the body of the earth, the great slow chimes of the planet itself. And in those echoes, in the faint and patient sound of the world ringing like a struck bell, we found the iron heart, measured it, and one day, by listening to the very same earthquakes again, decades later, we heard it change. But that is getting ahead of ourselves, and tonight, there is no need to hurry anywhere. We have all the time in the world. So let us simply rest here for a moment, at the top of the descent, with the picture held gently in mind. A ball of iron the size of Pluto, hotter than the face of the sun, frozen solid by the weight of an entire planet, pressing inward, floating in an ocean of liquid metal, turning once a day with the rest of the world, while drifting by a hair forward and then back across the slow span of 70 years, sealed away beneath 6,000 kilometers of stone and fire, somewhere none of us will ever go, and known to us in all its detail only because we learned patiently over more than a century to listen to the sound of the earth itself. In a moment, we will begin to go down. We will follow the sound. We will meet the people who first learned to read these echoes, the quiet, careful minds who sat with the faint traces of distant earthquakes and slowly, line by line, drew a map of a world no one could see. We will learn how a wave of motion travels through the planet, how it bends and splits and casts shadows, and how from those shadows a single woman, working alone in the early part of the last century, inferred the existence of the very iron ball we have been speaking of, simply from the way the sound arrived where it should not have. We will trace the long, slow story of how we came to know the heart of our own world. But none of that needs to begin just yet. For now, let the weight settle, let the breath lengthen. Far below you, deeper than any hole we have ever dug, deeper than the deepest ocean, deeper than thought can easily follow, the iron heart of the earth is turning. It has been turning since long before you were born, and it will be turning long after this night is forgotten. It is hot enough to be a piece of the sun, and yet it is calm and solid and slow. It does not race, it does not panic. It keeps its own ancient time, forward and then gently back, across the patient decades. And tonight, as you rest, it is turning still, quietly, far beneath you, carrying you and everyone you love through the dark at the steady, unhurried pace it has always kept. So let us go down to it, slowly, together. There is no rush. The iron heart is not going anywhere, and neither are you. Just breathe and listen, and let yourself begin to sink, the way the slow crystals of that distant sphere have been sinking and settling for longer than there has been a single living thing to wonder about them. Begin with the size of it, because the size is the first wonder. Picture, if you can, a sphere of solid iron and nickel, a single piece of metal with a radius of about 1,220 kilometers. That is roughly 2,400 kilometers from one side to the other. It is hard to hold a number like that in a drowsy mind, so let me give you something to set it against. There is a small, cold world out at the far edge of our solar system, a world we once called the 9th planet, and now call a dwarf planet, Pluto. Its mean radius is about 1,188 kilometers, which means the iron ball at the center of the Earth is very slightly larger than Pluto itself, a whole frozen world, a dwarf planet of metal sitting silent at the core of the ground you are lying on. Let that image rest in the dark for a moment. Not out there, in the cold distance where the telescopes point, but down here, beneath the floor, beneath the soil, beneath the rock and the deeper rock. A sphere the size of a planet, made of iron, held at the center of everything. And here is where the wonder deepens, where it becomes a paradox that the half-sleeping mind can turn over gently, the way you might turn a smooth stone in your hand. That iron ball is not cold the way the distant Pluto is cold. It is hot. It is extraordinarily hot. The temperature at the heart of the Earth is somewhere around 5,400 degrees. To give that a shape you can feel, look up in your imagination at the surface of the sun. The bright face of the sun that we are told never to look at directly, the photosphere, sits at around 5,500 degrees. So the iron heart of our planet is nearly as hot as the surface of the sun, a piece of the sun's own fire buried under your feet. And yet, and here is the strange and beautiful turn, it is solid. Not molten, not glowing and flowing like lava, not a churning sea of fire as the films would have you believe. Solid. Frozen in its way. A crystal. How can something nearly as hot as the surface of the sun be solid as rock? The answer is pressure, and the answer is one of the quiet marvels of the deep. Down there at the center, the weight of the entire planet presses inward from every direction at once. Every kilometer of rock and metal above it bears down, and it all adds up to a pressure of around 330 to 360 gigapascals. The word is hard to feel, so set it aside and keep only the meaning. It is more than 3 million times the pressure of the air around you right now, the air you are breathing slowly in and slowly out. 3 million atmospheres squeezing inward. And pressure does something to metal that you might not expect. It changes the rules. We tend to think of melting as a matter of heat alone, that you warm a thing enough and it turns to liquid, but the temperature at which iron melts is not fixed. Squeeze it hard enough and you raise that melting point higher and higher. Under the crushing weight at the center of the Earth, the temperature at which iron would melt climbs above the temperature that is actually there. And so the iron, hot as it is, hot enough to be a piece of the sun, cannot melt. It has nowhere to go. The pressure holds it together, locks it into place, freezes it solid, not in spite of the heat, but in defiance of it. The deepest place on Earth is one of the most extreme, and yet it is held in a kind of perfect stillness, a hot crystal pressed into being by the weight of the world. So when you hear that the heart of the Earth has changed direction, set aside, gently, the picture that the words first conjure. Set aside the alarm, because the truth is far quieter and far stranger than the headline suggests. The iron ball did not stop. It did not reverse itself in the way you might imagine, swinging round like a great wheel, grinding to a halt and turning the other way. In absolute terms, against the distant stars, it never stopped at all. It still spins with the rest of the planet once around every day or so, the same turning that brings you your mornings and your evenings, your light and your dark. What changed is something far more subtle. The iron ball does not sit rigidly fixed inside the Earth. It floats, nested within a vast ocean of liquid metal, free to turn at a slightly different rate than the solid rock above it. For a long stretch of years it had been creeping forward, just barely, a fraction of a degree faster than the mantle around it, racing ahead by the smallest of margins. And what the careful listeners noticed is that this tiny lead slowed, it eased. Around the year 2009, by their reckoning, that small forward creep came to a near standstill relative to the ground above, and then it appears to have begun to drift gently the other way, falling a little behind instead of running a little ahead. Differential rotation, the scientists call it. A change measured only against the mantle, never against the sky. The heart of the Earth did not stop. It simply changed by the faintest amount how it moves in relation to the rock that wraps around it. A slow, patient rocking, forward and then back, the way a thing settles when it has been turning for a very long time. Before we go any deeper, let me ask something of you softly, the way you might ask it of a friend lying near you in the dark. Tell me, if you would like to, where in the world you are listening from tonight. What country, what city, what quiet room. There is something I find comforting in imagining all of you scattered across the surface of this turning planet, each above the very same iron heart, each carried at the very same unhurried pace. And if you are new here, if you have only just found your way to this slow corner of the night, you are welcome to stay. Subscribe if it suits you, and there will be more of these long, quiet descents waiting whenever you cannot sleep. But there is no hurry in any of it. Stay only as long as it pleases you and drift off whenever you like. For tonight, we are going all the way down, slowly, to the center of the Earth, to the iron ball the size of Pluto, hotter than the sun and frozen solid, gently changing the rhythm of its turning far beneath us. And we will take our time getting there, because the journey itself is the rest. But here, at the very start, a question waits, and it is perhaps the strangest question of all. How can we possibly know any of this? No one has ever been there. No one ever will. The deepest hole that human beings have ever dug into the body of the Earth is a place called the Kola Superdeep Borehole, drilled patiently over many years in the far north. After all that effort, it reached a depth of about 12.25 kilometers. 12 kilometers into a planet whose center lies some 6,370 kilometers down, which means our deepest reach, our greatest digging, our most determined plunge into the ground carried us barely 0.2% of the way to the heart. We scratched the surface and stopped and could go no further. Everything else, all of it, the size and the heat and the slow turning of that iron ball, we learned without ever touching it at all. And so we arrive at the method, the one instrument that has reached, in a sense, where no drill ever could. Not a physical probe, not a robot arm, not a camera lowered on a wire into the dark. The instrument is sound, specifically the sound of the Earth breaking. When the ground tears along a fault, when rock that has been pressed against rock for centuries finally gives way and slips, the energy released moves outward through the planet in waves. Not just along the surface, the rolling, heaving waves that tumble buildings and ring church bells, but downward and inward, deep into the body of the world, following curved paths through layers of different density, bending and reflecting and splitting and arriving, minutes later, at seismograph stations on the other side of the globe. The planet, in other words, rings when it is struck. Not loudly. Not with a sound any ear could hear without instruments. But the ringing is real, and it carries information, and that information, read carefully and over a long time, is how we built our picture of everything that lies below. There are two kinds of waves that matter most to this story. The first are called P waves. The P stands for primary because they arrive first, racing ahead of everything else, moving through the Earth at speeds that would seem extraordinary in any other context. A P wave is a compressional wave, which means it pushes and pulls the material it moves through in the same direction it is traveling. Imagine a spring laid out along a table. Push one end and a compression, a momentary crowding together of the coils, travels along the length of the spring and emerges at the other end. That is what a P wave does to rock, to liquid iron, to whatever it encounters on its journey. It squeezes and expands, passing the energy forward. The crucial thing about P waves is that they can move through anything. Solid rock, liquid metal, even the dense iron-nickel soup of the outer core that we will come to shortly. They are not fussy. They propagate through any material that can be compressed, and almost everything in the deep earth can be compressed, at least a little. The second kind are called S waves. The S stands for secondary or sometimes shear, and they arrive after the P waves because they are slower. An S wave moves differently. It shakes the material it travels through from side to side, perpendicular to the direction it is going. Think of shaking a rope tied to a wall. The wave that travels along it is a shear wave, a sinuous ripple moving sideways. S waves, unlike P waves, can only travel through solid material. A liquid cannot sustain a shear. There is nothing to grip, no rigidity to propagate the sideways shake. And this is a crucial distinction because it is exactly this difference, which waves arrive, which waves are absent, and how they are timed, that told us, without any drilling, what the inside of the Earth is made of and whether it is solid or liquid. When seismologists began in the late 19th and early 20th centuries to build networks of recording stations around the world and to study the waves arriving from distant earthquakes, they noticed something strange. There was a region on the other side of the planet from any given earthquake, a broad arc, where P waves arrived only faintly, if at all. This region became known as the seismic shadow zone. The waves should have traveled in straight lines, or nearly so, and arrived clearly. Instead, they were deflected, bent away, as if they had encountered something different deep inside the Earth, something with a different density, a different character, a different speed. The shadow told them something fundamental about the planet's interior. In 1906, a British geologist named Richard Dixon Oldham was studying the records of a large earthquake that had struck in 1897, and he made a careful observation about the pattern of wave arrivals at stations around the world. He noted that both P waves and S waves behaved oddly at certain distances, arriving later than expected and with altered character, and he concluded that there must be a distinct region at the center of the Earth, a core, with significantly different properties from the surrounding mantle. He did not know yet whether it was liquid or solid. He did not have all the details right. But he had, from the signatures of distant earthquakes, inferred that something separate and fundamental lay at the planet's heart. It was the first time anyone had reached that conclusion from evidence rather than speculation. Then in 1913, a German seismologist named Benno Gutenberg refined the picture considerably. Working through the seismograph records of many earthquakes from many different stations, he was able to calculate with reasonable precision the depth at which the mantle in the vast rocky middle portion of the planet gave way to the core beneath. This boundary, this transition zone deep underground where rock becomes metal, became known as the core mantle boundary, sometimes abbreviated to CMB. Gutenberg placed it at roughly 2,900 kilometers below the surface, a figure that remains, over a century later, not far from modern estimates. He had found, by listening to the echoes of earthquakes, the outer edge of the metallic heart. But the core, as Gutenberg understood it, was a single thing, one region distinct from the mantle, sitting at the center. It was only 2 decades later that someone looked more closely at the records and realized the picture was still incomplete. Her name was Inge Lehmann. She was a Danish seismologist working in Copenhagen, and she is, in the history of Earth science, one of those rare figures who achieved something decisive and essentially alone. In the 1930s, Lehmann was examining the records of a large earthquake that had struck near New Zealand in 1929, and she noticed something that other researchers had overlooked or explained away. There were P waves arriving in the shadow zone, the region where, according to the existing model, they should not have appeared in any meaningful strength at all. They were weak, but they were there. Something was sending waves into the shadow, which could only mean that something inside the core was reflecting or refracting them in a way the simple, uniform core model did not predict. She sat with the data, and she thought. And she reasoned her way to a conclusion that was, in retrospect, as clean and elegant as any inference in science. If there were a solid sphere nested inside the liquid outer core, a hard inner ball with a higher wave speed, then some of the P waves diving deep into the planet would strike that inner boundary, refract through it at a different angle, and emerge on the far side of the Earth in exactly the regions where they were, puzzlingly, showing up. The shadow was not empty. It was lit by waves that had taken a deeper path, been bent by a hidden boundary, and arrived late from below. She published this in 1936 in a paper of almost legendary brevity and confidence. The paper's title was simply 2 characters, P. That was all. The notation she used for the waves that had passed through her proposed inner sphere. No elaborate title, no lengthy argument, just the observation, the reasoning, and the conclusion. The Earth has a solid inner core, we know because of how it bends sound. Lehmann was later described by a contemporary as the only person in the world who could argue with Benno Gutenberg and win. She lived to be 104 years old, long enough to see her discovery confirmed and elaborated beyond anything she could have imagined in 1936. But the essential insight was hers, and it was drawn not from any direct measurement, not from any physical sample, but purely from the geometry of echoes. Now we had the structure, a rocky mantle, enormous and deep, reaching down nearly 2,900 kilometers from the surface. Below it, the outer core, liquid iron nickel, roughly 2,200 kilometers thick, a vast ocean of molten metal wrapped around the very heart. And within that liquid ocean, nested at the center, the solid inner core, about 1,220 kilometers in radius, slightly larger than Pluto, sitting in stillness, or what appeared, for decades, to be stillness, at the center of the world. But why is there a liquid layer at all? Why does the outer core remain molten when the inner core, at the very same depths or deeper, is solid? The answer is pressure, the same answer we met earlier when we asked how something hotter than the sun's surface could possibly be frozen. The outer core is also extremely hot. Temperatures there run into the thousands of degrees, but the pressure at the boundary between mantle and outer core, while immense, is not quite enough to push the melting point of iron above the local temperature. The iron there remains liquid as the ocean, but far denser, far hotter, and far more electrically conductive. This matters enormously for what happens next, because that liquid iron is not sitting still, it is moving, driven by the heat rising from below, shaped by the rotation of the Earth and by compositional differences as lighter and heavier materials separate under gravity. The outer core churns in vast, slow, convective patterns. Iron rises and falls in enormous currents, spiraling and looping through a space the size of a small planet. And it is this motion, at this perpetual, slow churning of an electrically conductive fluid, that generates something we all depend on and most of us never think about: the Earth's magnetic field. The process is called the geodynamo. It works by a principle that should be familiar from any school physics class, even if the scale of it here beggars the imagination. When an electrically conductive material moves through a magnetic field, it generates electric currents, and those electric currents in turn generate a magnetic field. A self-sustaining cycle in which motion produces magnetism and magnetism shapes the motion, running continuously as long as the fluid keeps moving and the heat keeps driving it. The outer core, in its constant churning, is the engine of a dynamo that wraps the whole planet in an invisible magnetic shield, the magnetosphere, deflecting the charged particles streaming from the sun, protecting the atmosphere from being slowly stripped away, and enabling life on the surface to exist without being bathed in radiation. It is worth pausing here in the dark and letting that sink in. The magnetic field that keeps us safe, that makes compass needles swing north, that steers migrating birds across continents, that prevents the solar wind from slowly dismantling our atmosphere. All of it is powered by the motion of liquid iron 2,900 kilometers beneath our feet. We stand on thin rock beneath an open sky, and somewhere far below us a storm of metal moves in slow spirals, and its turning is why we are here. Now the inner core sits inside all of this. It is nested within the liquid outer core the way a stone sits in a river, surrounded on all sides by moving fluid, not touching the mantle above it directly, separated from the solid rock of the planet's middle layers by that deep ocean of iron. And this is the key to understanding why it can rotate differently from the rest of the Earth. There is no solid connection. Nothing locks the inner core mechanically to the mantle the way one gear locks to another. The coupling between them is magnetic and gravitational. Real, significant, but not rigid. It is a soft coupling, a remote influence, not a hard physical link. And because of that softness, the inner core can, in principle, turn at its own pace. Slightly faster, slightly slower, or perhaps, as the most recent evidence suggests, slightly ahead and then slightly behind, oscillating over decades. We will come to the turning in full. But before we do, there is one more thing about the inner core that the seismic waves revealed, and it is something that, the more you consider it, the stranger it becomes. The inner core is not uniform. It is not a simple iron ball with the same properties in every direction. The seismic waves tell us otherwise, and they tell us in a subtle but unmistakable way. Waves that travel through the inner core from pole to pole, entering near the north, exiting near the south, or vice versa, travel a few % faster than waves that travel through it equatorially, cutting through in the direction of the tropics. A few % is not a casual discrepancy. In a body of that size, a few % difference in wave speed translates to a meaningful structural asymmetry. The inner core, for reasons that are still not entirely settled, responds differently to sound depending on which way the sound is going. This property has a name: anisotropy, from the Greek for unequal directions. An anisotropic material is one whose properties are not the same in all orientations. Wood is an everyday example. Wood is easy to split along the grain and difficult to split across it. The fibers align in one direction, and that alignment changes how the material behaves depending on how you attack it. The inner core appears to have something analogous, not literal grain in the timber sense, but a preferred alignment of its iron-nickel crystals, a large-scale structural ordering that runs, preferentially, in the direction of Earth's rotation axis, from pole to pole. This was first clearly established in the mid-1980s, principally through work by Alberto Morelli, Adam Jablonski, and John Woodhouse, who reported in 1986 that the global seismic data consistently showed this polar equatorial asymmetry. Then Kenneth Krieger, in 1992, refined the measurements and confirmed that the inner core's anisotropy was real and robust, not a statistical artifact or a quirk of data coverage. The effect was there. The iron crystals inside the inner core, crystallized iron under pressure so immense that it takes on a hexagonal or body-centered cubic structure, quite unlike ordinary iron at room pressure, appeared to be aligned systematically on a planetary scale. Think about what that implies. The inner core is solid, yes, but it is not static. Over geological time, over millions and billions of years, The iron inside it must have moved or been growing in such a way that the crystals ended up oriented preferentially. A solid that flows. A crystal structure built up over an immense time scale, slowly, millimeter by millimeter and year by year. The alignment is a record of process. It is a memory locked into the iron of how the core grew and possibly how it moved. There is something deeply calming in this image if you let it settle. The inner core, which from the outside might sound like a static, inert lump of metal, just sitting there at the center, doing nothing, is in fact a slowly evolving structure. Its crystals are oriented, its waves travel differently in different directions. Its outer edge is growing 1 millimeter per year, crystallizing outward from a liquid ocean that surrounds it. And inside that outer growth, the older, deeper iron carries a structural memory of all the time it has been there. Perhaps 500 million years, perhaps 1.5 billion, perhaps more. None of this was visible from the surface. None of it could have been guessed from geology or chemistry or any measurement taken on land. All of it came from listening, from placing delicate instruments at points around the globe, waiting for the planet to shake, and then reading the tiny differences in how long the waves took to arrive and from which directions and with what amplitudes. The inner core, in all its complexity, was built entirely out of the echoes of catastrophe. The earthquakes, which are among the most violent natural events our planet produces, also happen to be the only X-ray machine we have capable of seeing to its center. And here is where the story begins to deepen into something stranger still. Because for decades after Lehmann's discovery and after the anisotropy findings, the inner core was assumed to be simply there, the same from year to year, rotating with the rest of the planet as a single unified object. No one really questioned whether it might be spinning at a different rate. Why would you? It was solid, it was deep. It seemed, from everything we knew, to be a permanent feature, fixed and stable, one of the most permanent things on Earth. It was only when people began comparing seismic records from different decades, particularly records of what are called repeating earthquakes, that the question of differential rotation even arose. And to understand what a repeating earthquake is and why it matters so much to this story, it helps to think about what an ordinary earthquake is not. An ordinary earthquake, recorded once, gives you one snapshot of the wave paths through the interior. You can measure the wave speeds, the travel times, the amplitudes, but you cannot easily separate what is being caused by the structure of the interior from what is being caused by the specific location and geometry of that one earthquake. The earthquake source is never perfectly known. The station positions introduce their own small errors, and the result is a measurement that is accurate in broad outline but imprecise in fine detail. A repeating earthquake is different. It is, as the name suggests, an earthquake that occurs again and again at essentially the same location in essentially the same way, generating essentially the same seismic signature. There are places on Earth where the same fault segment ruptures repeatedly, producing nearly identical earthquakes separated by years or decades. The South Sandwich Islands, a remote arc of volcanic rock in the far South Atlantic, is one of the best-known examples. Seismically active, geologically consistent, producing quakes whose waveforms, when compared across time, are remarkably similar. Not identical, but similar enough that any differences in the waveforms recorded at a distant station can be attributed not to variation in the source, but to changes in what the waves pass through on their way. When those waves cross the inner core, they are sensitive to the inner core's structure. If the inner core has rotated, even fractionally, then the waves are crossing a slightly different slice of it than they did the last time the same earthquake occurred, and the waveforms, scrutinized carefully, can reveal that shift. It is like playing the same note on a piano twice, years apart. If the note sounds different the second time, something about the instrument has changed. And if you know the piano well enough, you can infer what. The repeating earthquakes of the South Sandwich Islands recorded at seismic stations in Alaska, chosen because the geometry of source and receiver places the wave paths directly through the inner core, became the key dataset. Not the only one, but the most clearly diagnostic. Pairs of quakes, separated by years or decades, the same source, the same receiver, the same path, but subtly different waveforms arriving at the end. Something between the South Atlantic and Alaska had shifted. Something inside the planet had moved. It was this kind of data that led in 1996 to the first bold claim that the inner core was spinning faster than the rest of the Earth, what geophysicists call superrotation. Xiaodong Song, working at Columbia University's Lamont Doherty Earth Observatory with Paul Richards, published the claim in Nature. The inner core was rotating about 1 degree per year faster than the mantle. 1 degree sounds small, but over a year for a sphere 1,220 kilometers in radius, it adds up to a measurable positional shift, and over decades it would accumulate into something significant. The claim was electrifying. The inner core not merely sitting still, but actively spinning ahead, outpacing the planet around it. But the scientific community rightly did not simply accept it. The measurement was on the edge of detectability. Other researchers examined the data and offered alternative interpretations. Some suggested the waveform changes might reflect changes at the surface of the inner core. Small irregularities, bumps and depressions moving in and out of the wave path, rather than a true bulk rotation. Others questioned whether the repeating earthquakes were truly identical enough in their sources to make the comparison clean. Over the following years, the estimated rate of superrotation was revised steadily downward. 1 degree per year became a fraction of a degree. The debate refined, as scientific debates do, into a more nuanced and less dramatic but more honest picture. Yes, there was probably some differential rotation. Yes, the inner core was probably not locked perfectly to the mantle. But the rate was slower, the uncertainty was larger, and the question remained genuinely open. And then came the next, quieter chapter of the story. The one that began to suggest the rotation was not just slower than originally claimed, but that it was changing. The word that seismologists use for the technique, the foundational technique that made any of this knowledge possible, is almost poetically simple. They listen. They listen to the planet. When an earthquake ruptures along a fault, the energy released does not travel in a single wave in a single direction. It radiates outward in all directions at once, a sphere of compressed and shearing energy expanding through the body of the earth, the way a sound moves through still water after a stone is dropped. And those waves, like sound, are shaped by the material they pass through. They bend, they slow, they refract. In some materials, certain kinds of waves cannot travel at all. And it is precisely in these distortions and absences and slowings that the planet's interior structure is written, if you know how to read it. There are 2 primary kinds of body wave, and their names are almost self-explanatory once you hold them in mind for a moment. P waves are compressional. They travel by squeezing and expanding the material ahead of them, the way sound moves through air, a series of compressions and rarefactions propagating forward. P waves can travel through solids and through liquids alike. They are fast and they are indifferent to the phase of the material they cross. S waves are shear waves. They move by pushing the material sideways perpendicular to the direction of travel, and they depend absolutely on the rigidity of what they are moving through. A liquid has no shear rigidity. A liquid cannot be pushed sideways and hold that displacement long enough to pass it forward, and so S waves stop dead at the boundary of any liquid region. This simple physical fact became the key to the outer core's secret. When seismologists mapped where S-waves arrived after large earthquakes and where they were entirely absent, they found a vast shadow zone. There were regions of the globe where, for certain earthquake sources, no S-wave signal arrived at all, no matter how sensitive the instruments. The only explanation consistent with the geometry was a large liquid region at the Earth's center, a zone where shear waves simply ceased. The outer core was liquid. The disappearance of S-waves announced it. Richard Dixon Oldham, an English geologist working with the Geological Survey of India, was the first to clearly demonstrate in 1906 that the Earth has a distinct central core, using observations of the way P-wave and S-wave travel times deviated from what uniform material would predict. He could not say precisely what lay at the center, only that something different was there, something that bent the waves in ways inconsistent with a simply layered homogeneous body. The core existed. Its nature remained uncertain. Benno Gutenberg, a German-American seismologist of remarkable precision, located the boundary between the outer core and the mantle in 1913. He determined it at a depth of approximately 2,900 kilometers below the surface, a boundary now known as the Gutenberg discontinuity, or the core-mantle boundary. His estimate, made more than a century ago from laborious hand calculations and comparative travel timetables, was within a few kilometers of the values modern seismology confirms. The outer core had a top, a defined surface, a place where the churning liquid metal of the deep began. But what lay below it, deeper still within the liquid, that remained unresolved? And then in 1936, a woman working alone in Copenhagen read the planet's innermost secret in the shape of a wave that should not have existed. Her name was Inger Lehmann. She was Danish, meticulous, and possessed of a patience with data that her contemporaries found extraordinary. She had been working with seismograms from a large New Zealand earthquake in 1929, and she noticed something in the records from stations at particular distances from the epicenter. There were P-wave arrivals appearing in what seismologists had assumed was a shadow zone, a region where the curvature of the outer core's liquid should have deflected all waves away, leaving silence. The arrivals were faint. They were anomalous. They were, by the prevailing model, impossible. Lehmann did not dismiss them as instrument noise or transcription error. She sat with them. She reasoned that if a wave was arriving inside the predicted shadow zone, it had to have come through something different, something inside the liquid outer core that bent the wave's path. If there were a second boundary deeper within the core, a boundary where the material changed properties again, some waves would refract differently, curve back upward, and emerge in places the simple two-layer model said they could not reach. The anomalous arrivals were not noise, they were signals. They were the echoes of a hidden solid sphere nested inside the liquid ocean of the outer core. She published her findings in 1936 in a paper of almost brutal brevity and directness. The title was, in full, P, nothing more. In the notation of the time, P referred to the P waves that had passed through the core. And in those two characters, that single letter with its single mark, Lehmann had compressed the discovery of the Earth's solid inner core, the innermost object in the world, a finding that still stands today as one of the most elegant inferences in the history of geophysics. She had seen a sphere inside a sphere, a solid heart beating within a liquid ocean, and she had seen it only by listening to the shadows that earthquakes cast through the planet. It took time for the community to fully accept her model, as it always does. But the evidence accumulated in her favor over the following decades, and by the mid-20th century, the basic architecture she had proposed was established. The planet had layers, a solid inner core, a liquid outer core, the mantle above, and the nature of those transitions, the precise depth and character of each boundary, was being measured with ever finer instruments and ever larger datasets of earthquake records. The outer core, the liquid ocean wrapped around Lehmann's solid sphere, is approximately 2,200 kilometers thick. Its composition is predominantly iron and nickel, the same heavy elements that dominate the inner core, but here, at these depths, but under pressures slightly less overwhelming than those at the planet's very center, the melting point of iron is below the local temperature. The material flows. It convects. Hot fluid rises near the inner core boundary, cools slightly as it moves outward toward the mantle, then sinks again in great slow plumes and sheets and eddies. And within this convecting metal sea, the rotation of the Earth imposes structure. The Coriolis effect organizes the flow into columns and spirals aligned with the planet's spin axis, great columnar convection cells turning and rising and falling in the metallic dark. It is this organized motion, this churning of conducting fluid in a rotating system, that generates the magnetic field, the geodynamo. The liquid outer core is, in the most literal physical sense, the generator of the invisible shield that surrounds the entire planet, the magnetosphere that deflects the solar wind, that protects the atmosphere from erosion, that makes the surface of the Earth habitable. And the inner core, because it is nested inside this liquid and decoupled from it by the fact of its solidity, floats within that ocean electromagnetically and gravitationally, free to rotate at its own rate. Not entirely free. The coupling between the liquid outer core and the solid inner core, both electromagnetic and gravitational, ties them loosely together. But loosely is the operative word. There is no rigid mechanical connection forcing the inner core to match the mantle's rotation exactly. It can deviate. And the question, the slow accumulating seismological question that Song and Richards opened in 1996, was by how much it deviated and in what direction, and whether that deviation was constant or changing. The iron crystals inside the inner core offered another line of evidence, one that came not from the rotation question directly, but from a related strangeness. Seismologists mapping travel times very carefully found that P waves moving along the Earth's rotation axis from pole to pole through the inner core arrived slightly faster than P waves traveling through the equatorial plane. The difference was small but consistent, a few percent. Material properties that vary with direction are described as anisotropic, and the inner core is anisotropic in a way that points to large-scale structure inside the solid. The most natural explanation for this anisotropy is that the iron crystals inside the inner core are aligned preferentially. Iron at the extreme pressures and temperatures of the inner core takes on particular crystalline forms, and if those crystals are not randomly oriented but instead aligned along a common axis, they will transmit seismic waves differently in different directions, the way wood grain transmits sound differently along and across the fibers. Something inside the inner core, whether convective flow, magnetic forces, or the accumulated history of the core's slow growth, had aligned the crystals. And because waves were faster pole to pole, the alignment was roughly parallel to the Earth's spin axis. Morelli, Givonsky, and Woodhouse first documented this in 1986. Kenneth Krieger confirmed and refined it in 1992. The inner core was not merely a solid ball of iron, it was a structured solid with texture and grain, like a vast and ancient piece of metal that had been slowly worked into alignment by forces operating over geological time. And it was that structure, that inner grain and alignment, that made the next question almost unavoidable. If the crystals were arranged along the rotation axis, and if the inner core was surrounded by a liquid outer core through which it floated freely, uncoupled from the mantle above by that vast, swirling ocean of metal, then was the inner core actually rotating at the same rate as everything else? Was it locked to the planet, turning with it as a single, rigid body? Or was it doing something else, something slower or faster, drifting in its liquid cradle by a fraction of a degree each year? The question had been forming quietly in seismology since the 1980s, sharpened by the anisotropy findings. If the grain of the inner core's crystals was not perfectly aligned with the rotation axis, if it was tilted by a few degrees, then as the core rotated relative to the mantle, seismic waves passing through it at different angles would arrive with slightly different travel times. The tilt of the crystal alignment would act as a signature, a marker moving slowly across the planet's interior. And if you could measure the shift in that signature over years or decades, you could infer the rotation rate. It was a subtle and elegant idea. It was also extremely difficult to test because the signals involved were tiny and the Earth itself was not a controlled laboratory. But in 1996, two seismologists decided to try. Xiaodong Song was at Lamont Doherty Earth Observatory, affiliated with Columbia University. Paul Richards was his colleague there, a seismologist of long experience and meticulous habit. Together they combed through decades of seismic records, comparing the arrival times of P waves that had passed through the inner core along similar paths at different times. What they found, they reported in Nature that same year, was a shift. The seismic waves seemed to be arriving slightly faster along certain paths than they had in earlier decades, which, if interpreted as the crystal signature rotating relative to the recording stations, implied that the inner core was outpacing the mantle above it. It was spinning ahead, they proposed, by roughly 1 degree per year. 1 degree per year, that sounds small, and in human terms it is, but in geophysical terms it was remarkable. If sustained, 1 degree per year meant the inner core would complete a full extra rotation relative to the mantle in about 360 years. The solid ball of iron at the center of the world was not locked to the planet the way a pit is locked inside a cherry. It was doing something of its own. The concept acquired a name almost immediately: super-rotation. The inner core was super-rotating, outrunning the mantle by a tiny but measurable margin. The finding attracted enormous attention, and with attention came scrutiny. Other researchers tried to replicate or extend it. Some found supporting evidence, some found conflicting evidence, and some questioned the interpretation of the data altogether. Seismic waves passing through the inner core are sensitive not just to rotation, but to anything that might alter the crystal structure or the wave speed, including changes at the inner core boundary itself, heterogeneities in the outer core, or problems with the assumption that the earthquake source locations had not shifted between the measurements. The 1 degree per year figure began to erode under examination. More careful analysis using more data and more sophisticated techniques revised the rate downward. Not 1 degree per year, it seemed, but a fraction of a degree. Perhaps a tenth, perhaps less. The super-rotation was still there in the data for many researchers, but it was smaller and quieter than the original estimate. And here the story entered a long, careful, somewhat contentious period of scientific revision. Through the late 1990s and the 2000s and into the 2010s, different teams using different data sets and different methods came to different conclusions. Some studies found super-rotation persisting at modest rates. Others found no rotation at all, or rotation that varied with time. It was the kind of scientific landscape that looks from the outside like confusion, but from the inside is the normal progress of a field grappling with genuinely difficult signals embedded in noisy data from an inaccessible object. Nobody could go down there and attach a gyroscope. Everything had to be inferred from sound, and the sound was subtle and the interpretations were difficult. The field waited for a cleaner method, or more data, or both. The cleaner method, it turned out, had been available all along. It just required enough patience to let time accumulate enough pairs. The technique is called doublets, or more precisely, repeating earthquakes. The idea rests on a simple and elegant observation. Most earthquakes are unique events. A fault ruptures in a particular way at a particular moment, and the wave pattern it produces reflects the specific geometry of that rupture. But in certain regions where tectonic stress builds and releases along very similar fault planes, earthquakes can recur in nearly the same location, with nearly the same mechanism, producing wave patterns that are almost identical. If you record such an earthquake in 1970 and then another earthquake from the same location in 1995, the two wave patterns should be nearly indistinguishable. They should be the same note, struck by the same string, at two different moments, unless something changed along the path between them. If the inner core has rotated between the two earthquakes, the wave that traveled through the inner core in 1995 will have traveled through a slightly different orientation of crystal structure than the wave that traveled through in 1970. The waveform will have shifted very slightly in its shape or its timing. And because everything else, the source location, the fault mechanism, the receiver stations, has stayed essentially fixed, the only explanation for the shift is a change in what the wave passed through. The inner core became the instrument, and the repeating earthquakes became the repeated note that let you hear if the instrument had moved. The region that turned out to be most valuable for this purpose was a cluster of seismic activity around the South Sandwich Islands, a remote archipelago in the South Atlantic, deep in the cold waters of the Southern Ocean. The islands are volcanic, perched on a tectonic plate boundary, and they generate small earthquakes with remarkable consistency from very similar locations along the same fault systems, year after year, decade after decade. Those small, consistent earthquakes sent their waves around the planet, and many of those waves traveled through the inner core on their way to recording stations in Alaska, on the opposite side of the globe. Alaska, with its own seismically active terrain and its long history of careful instrumentation, had been recording earthquake waves for decades. The combination, a persistent source in the South Atlantic, a reliable receiver in the far north, and decades of accumulated records, made it one of the most powerful natural listening posts for the inner core that exists. Xiaodong Song continued working with these doublets through the 2000s and into the 2010s. By 2023, he had a long-time collaborator in the work, Yi Yang, also at Peking University, where Song had moved. Together, Yang and Song assembled a dataset of repeating South Sandwich Islands earthquakes spanning several decades, carefully matched for location and fault mechanism, and they compared the waveforms recorded in Alaska over that long sweep of time. What they found, they reported in January of 2023 in the journal Nature Geoscience, was not what anyone had quite expected. The super-rotation that earlier work had suggested, that slow drift of the inner core ahead of the mantle, had not continued steadily. The waveform changes that reflected the inner core's rotation relative to the mantle had grown, reached a kind of maximum, and then stopped growing. Around the year 2009, the changes ceased accumulating. The inner core appeared to have reached a point where its differential rotation, its tiny lead over the mantle, had slowed to near zero. It was no longer getting further ahead. It had matched pace, briefly, with the mantle. And then the waveform changes began, slowly, to reverse direction, suggesting that the inner core was no longer even keeping pace, that it had begun to drift back the other way, falling slightly behind the mantle rather than racing ahead of it. The phrase that would go around the world in the following weeks was that the inner core had reversed direction, and in a carefully qualified sense, that is what Yang and Song reported. But the full picture was more nuanced, and in some ways, more interesting than any simple reversal. What Yang and Song proposed was not a sudden flip, not a violent change of state, but an oscillation. The inner core, they suggested, was engaged in a slow, back and forth, a rhythmic wobble in its rotation rate relative to the mantle, completing one full cycle, from leading to matching to lagging and back again in roughly 70 years. They called it a roughly 70-year oscillation, and the implication was that what had happened around 2009 was not a crisis or an anomaly, but simply the turning point in a long, slow rhythm that had probably been repeating for a very long time. Think of it like a pendulum that takes 35 years to swing one way and 35 years to swing back. No single moment on that arc is alarming. The pendulum does not stop, it does not break, it does not fall. It simply describes its arc over and over in the dark. And if you happen to observe it only at the turning point, at the instant it paused before returning, you might describe what you saw as the pendulum stopping and reversing direction. And you would be right, as far as that description went. But you would be missing the larger rhythm, the slow breath of the thing, the context that made the reversal not a sign of collapse, but a sign of life, of a system in motion. That context, the 70-year periodicity, it was the most important part of the 2023 paper, and it was the part most often lost in the excitement that followed. The popular accounts focused on the reversal, the changed direction, the stopped heart. The paper itself was at pains to describe it as a cyclic phenomenon, a feature of a dynamic system with no catastrophic consequence implied or expected. And here it is worth pausing, as this narration has paused before, to be precise about what changed direction. The inner core never stopped spinning. It never reversed in absolute space relative to the stars. It rotates with the planet, around and around every 24 hours, carried in the same great sweep that carries everything else. The oceans, the crust, the mantle, the outer core, you, your bed, the dark above your ceiling. What slowed and may have reversed was only the tiny differential, the fractional margin by which the inner core had been creeping ahead of the mantle. The inner core was, in this sense, not so much reversing as falling back from a small lead into a small lag. It was a change of a fraction of a degree per year, measured relative to the ground above, over a period of decades. That is the entirety of what changed. It is a delicate thing, a measurement at the edge of what seismology can resolve, and it is wondrous precisely because of its delicacy, not in spite of it. The year 2009 sits at the center of this story as a kind of quiet pivot. No earthquake marked it, no eruption, no storm, no visible sign of any kind reached the surface. The planet continued its business, the oceans moved, the seasons turned, the magnetic field fluctuated in its ordinary long way. People lived and built and wondered about other things entirely. Somewhere below all of that, in the liquid dark of the outer core, in the iron pressure at the very center, something made its slow turn, paused at the apex of its arc, and began the return. It was, in its way, as if the deepest part of the world took a long, slow breath and turned to come back. But science is not served by a single study, however careful. One team's result, however compelling, is not a conclusion. The field demanded confirmation, and it came from more than one direction. In 2022, a year before Yang and Song published, a team at the University of Southern California had been working on a related but distinct question using a completely different category of data. John Vidale and Wei Wang had turned to the records of underground nuclear test explosions, primarily American and Soviet tests conducted between 1969 and 1974. Those explosions, detonated deep underground at known locations and times, had sent powerful seismic waves through the planet, just as natural earthquakes did, and the records of those waves had been preserved in archives for decades. The advantage of nuclear tests as seismic sources was their precision. The location, the depth, and the timing were known with great accuracy, far more accurately than for most natural earthquakes. This made the resulting seismic signals very clean references. Wang and Vidal found, analyzing those archived explosion records and comparing them with natural earthquake data from later years, evidence of oscillation in the inner core's rotation, but on a different timescale. Their result, published in Science Advances in 2022, suggested a shorter cycle nested inside the longer one, something closer to 6 years, with the inner core alternately sub-rotating and super-rotating on that shorter rhythm. It was a different data set, a different method, a different team, and it pointed at the same fundamental picture. The inner core was not in a fixed rotational state, not locked, not perfectly steady, but oscillating, moving back and forth in its liquid housing on timescales from years to decades. The two oscillations, the roughly 6-year subcycle detected by Wang and Vidale, and the roughly 70-year longer cycle proposed by Yang and Song, might be harmonics of the same underlying dynamic, different notes in the same slow music. Or they might be independent modes of motion, each driven by different coupling forces between the core and the mantle above. The science was not yet settled on that point, but the convergence of evidence from independent groups using independent data sets was itself significant. Multiple lines of inquiry were pointing at the same central fact. The inner core moves, and its movement is not simple, not monotonic, not steady. Then in June of 2024, a third major corroboration arrived. Vidale and colleagues published again, this time in the journal Nature, using a combined dataset of repeating natural earthquakes and the old nuclear test records, covering a time span stretching from the 1960s through the early 2020s. Their analysis found, consistent with Yang and Song, that the inner core's rotation relative to the mantle had slowed and then reversed around the year 2010. They placed the turning point slightly later, but the picture was the same. The inner core had been running ahead, it slowed, it stopped gaining ground, and it began to backtrack. Their word for this was backtracking, and it carried the right connotation, not a catastrophe, not a reversal of the planet's spin, but the quiet reversal of a small lead, like a runner who had gotten slightly ahead of the pace and then settled back into it. The independent corroboration from Vidale's group was important not just for confirming the result, but for extending and refining it. Different researchers with different data sets arriving at the same conclusion is how provisional findings in geophysics become established facts. The inner core's rotation had slowed and reversed its tiny differential. That was now supported by multiple independent lines of evidence, spanning multiple datasets, multiple teams, multiple decades of seismic observation. It was not certain in the way that, say, the boiling point of water at sea level is certain, but it was far beyond speculation. And yet the scientific conversation around this result remained, and remains, genuinely open in important ways. Not everyone was convinced that bulk rotation of the inner core was the only or even the primary explanation for the observed waveform changes, a dissenting view which deserves to be taken seriously because it raises real and legitimate methodological concerns, argues that the changes in seismic waveforms recorded at Alaska from South Sandwich Islands earthquakes might not reflect the inner core rotating as a rigid body. Instead, they might reflect localized changes at or near the inner core boundary, changes in the topography of the boundary surface, or deformation of a thin, soft layer of material at the very top of the inner core. This alternative is not idle speculation. There are real physical reasons to think that the uppermost part of the inner core might not be perfectly rigid. The conditions at the inner core boundary, the precise threshold where liquid iron freezes into solid iron, are extreme and finely balanced. A small change in temperature or pressure at that boundary could locally melt or recrystallize the iron, changing its seismic properties without any rotation of the body as a whole. The waveform changes detected by repeating earthquakes would look similar whether the whole core had rotated or only the near-surface structure had changed. This uncertainty is real, and responsible scientists acknowledge it. Yang and Song acknowledged it in their 2023 paper. Vidale and colleagues discussed it in theirs. The debate is not between those who trust the data and those who do not, but between those who interpret the data as bulk rotation and those who think the signal might be more localized. Resolving that ambiguity is one of the active frontiers of the field, And the most recent work has, if anything, deepened rather than simplified that frontier. In 2025, Vidale and colleagues published new findings, this time in Nature Geoscience, reporting evidence that the inner core's surface itself may be changing shape over time, that the boundary between the solid inner core and the liquid outer core is not a fixed, rigid wall, but something that deforms, shifts, dimples, and swells on timescales of years to decades. This emerging picture, still being debated and examined, suggests that the inner core's outer surface may be more dynamic than previously thought, perhaps even slightly slushy or viscous in its outermost layers, with the transition from fully liquid to fully solid being gradual rather than sharp, and changeable rather than fixed. This is the science at its most recent and most uncertain edge. It is not established, it is emerging. It may be confirmed and refined by further work, or it may be revised, or part of it may prove to be an artifact of the data, but it hints at something important about the inner core's character. It is not a perfect billiard ball, hard and static inside its liquid shell. It may be a more complicated, more living object than the simple model suggests, with a surface that breathes slightly as the pressures and temperatures around it shift, with a rotation that oscillates, with a crystal structure that is anisotropic and textured and not fully understood. The neat layers of the Earth that every schoolbook diagram presents, the crisp concentric shells, each with clean edges, are approximations. The real Earth, at its deepest, is more subtle, more variable, and more strange. What remains clear in all of this, regardless of the unresolved details, is the larger picture. The inner core is not static. It is not simply sitting there, frozen and inert, an iron fossil at the bottom of everything. It moves. It breathes in its own geological rhythm. Its rotation relative to the mantle waxes and wanes over years and decades. Its boundary may deform. Its crystals are aligned in ways that record its history. And all of this motion, all of this subtle activity is connected to the larger working of the planet, to the flows in the liquid outer core, to the generation of the magnetic field, perhaps even to the tiny variations in the length of a day that geodesists have measured and puzzled over for years. The length of the day is not perfectly constant. You likely know this in the sense that leap seconds are occasionally added or removed from atomic time to keep clocks aligned with the Earth's actual rotation. But beyond those adjustments, there are slower variations, fluctuations of a few milliseconds in how long it takes the planet to complete one rotation, varying over periods of years to decades. These variations have been attributed in part to exchanges of angular momentum between the solid Earth and the atmosphere and oceans, and in part to processes inside the Earth itself. If the inner core is oscillating in its rotation relative to the mantle, that oscillation necessarily involves an exchange of angular momentum between the inner core and the rest of the planet. The inner core speeds up slightly, the mantle slows down by a corresponding tiny amount, and the length of the day changes by milliseconds, not hours, not minutes, milliseconds, over decades. This is, in its way, perhaps the most humbling detail of the whole story. The inner core contains roughly 1% of Earth's mass. It is enormous in absolute terms, a sphere the size of Pluto. But in proportion to the whole planet, it is small, and the forces it exchanges with the mantle are correspondingly subtle. Yet even at 1% of the planet's mass, oscillating by a fraction of a degree per year, it may be detectable in the length of the day. The Earth's timekeeping is sensitive enough that the slow rocking of its iron heart registers, in principle, at the surface. You would never feel it. You would never perceive the extra milliseconds accumulated over a year or over a decade. But the instruments know. And the knowledge that those instruments carry is itself a kind of wonder, the knowledge that the deepest interior of the planet and the ordinary turning of the day above are linked by invisible threads of angular momentum passing through the liquid metals sea. And it is worth remembering here, in the quiet and the dark, exactly how far away all of this is. The inner core begins roughly 5,150 kilometers beneath the surface. The deepest hole that human beings have ever drilled, the Kola Superdeep Borehole in what was then the Soviet Union, reached a depth of 12 kilometers and 2,600 meters before heat and pressure defeated the drilling equipment, and the project was abandoned in 1989, 12.26 kilometers. In the context of a journey to the inner core, that is less than 0.25% of the way. The boreholes, which took decades to complete and stood as one of the most ambitious engineering projects in human history, had barely scratched the crust. Everything below it, the lower crust, the mantle, the outer core, the inner core itself, remains as inaccessible as it has ever been. More inaccessible in many ways than the surface of Mars, which robotic spacecraft have reached and explored and sampled. The center of our own planet is farther from us in practical terms than the outer planets. We have sent signals past Pluto. We have not gone 1% of the way to our own center. And yet we know that is the genuine astonishment that sits underneath all the rest of the science. We know the radius of the inner core to within a few tens of kilometers. We know its temperature to within a few hundred degrees. We know the orientation of its crystal grain. We know that its rotation has slowed and may be reversing on a cycle that probably spans human generations. We know that inside it, at the very center, there is likely another layer, a hidden innermost heart with crystals pointing a different way. We know all of this from sound, from the echoes of earthquakes ringing through the planet at kilometers per second, arriving at seismograph stations after minutes of travel through rock and metal and liquid and crystal, carrying in their tiny timing shifts and waveform shapes the fingerprints of everything they passed through. The inner core speaks to us in the language of seismic waves, and because we have learned, slowly and painstakingly, to read that language, we can describe a world we will never see. And now we arrive at the deepest secret of all. Within the inner core, that Pluto-sized ball of iron-nickel, already hidden beneath nearly 6,500 kilometers of rock and metal and churning liquid, there is something else. A sphere within the sphere. A heart inside the heart. The idea has been circling in geophysics for more than 2 decades. In 2002, Miyake Ishii and Adam Jaworski, working with the same kind of careful seismic analysis that had revealed so much else about the deep Earth, noticed something unusual in how certain seismic waves behaved when they crossed the very center of the planet. The waves that traveled through the innermost region seemed to be doing something subtly different from the waves that crossed only the outer portions of the inner core. The anisotropy, the directional bias in wave speed, the faster travel pole to pole compared to equator, that had already told us the iron crystals inside were aligned like the grain in timber, seemed to shift. Not just diminish, but actually change orientation, as if somewhere below the already existing alignment, the crystals were pointing a different way entirely. It was a delicate inference, drawn from subtle differences in measurements that were already themselves at the edge of what instruments could reliably detect. The proposal was careful, tentative. There might, Ishii and Jaworski suggested, be a distinct innermost inner core, perhaps 600 kilometers in radius, nested at the very center of the larger, solid sphere. A ball within a ball within a ball. It was not dismissed. It was filed in the way that good science files ideas it cannot yet fully confirm as something worth watching. For the next 2 decades, it was watched. The difficulty is that to see something 600 kilometers across, buried beneath 5,000 kilometers of material, using only sound, you need sounds of exceptional quality and exceptional patience. Normal seismic waves from earthquakes crossed the inner core once, They enter on one side, curve through the interior, and exit on the other. That single crossing gives you information about the bulk of what was traversed, but blurs the fine structure. To read the innermost layer clearly, you would need waves that had passed through the center not once, but many times. Waves that had, in effect, bounced back and forth across the entire planet, each reversal sending them through the deepest point again. Such waves exist. When a large earthquake occurs, it sends energy rippling outward in all directions. Some of that energy travels to the far side of the planet, arrives at the antipode, the point directly opposite on the globe, and reflects back. Then reflects again. Then again. Each round trip takes roughly 18 to 20 minutes, depending on the wave type and path. After 5 full transits of the planet's diameter, a wave has been traveling for the better part of 2 hours, and it has crossed through the inner core 5 separate times. Each crossing deposits another layer of information, like a pencil line traced and retraced until the image sharpens. The problem is that 5 bounce waves are fantastically faint by the time they arrive. Each reflection loses energy, each kilometre of imperfect material absorbs a little more. By the time a seismic wave has crossed the planet 5 times, it carries only a whisper of its original amplitude, and picking it out of the background noise of a restless Earth is an act of extraordinary technical patience. In 2023, Thanh-Son, Pham and Hrvoje Tkalcic, working at the Australian National University, accomplished exactly that. They analysed seismic records from large earthquakes, quakes powerful enough to send coherent energy all the way around the globe multiple times, and identified the faint, multiple bounce signals that had traversed the planet's diameter up to 5 times. They read those signals for the directional bias, the anisotropy, that indicates crystal alignment. And what they found confirmed what Ishii and Dziewonski had first suggested more than 20 years earlier. The outermost shell of the inner core, the part that seismic waves have been crossing and recrossing for decades, has its crystals aligned roughly parallel to the planet's spin axis, pole to pole. Waves traveling that direction move faster by a few percent than waves traveling equatorially. This is the anisotropy that was first measured in the 1980s and confirmed many times since. But the innermost region, the central sphere of roughly 600 kilometers in radius, is different. Its crystals are tilted. They point in a different direction at an angle to the spin axis, as if whoever arranged the deep architecture of the Earth's heart had changed plans partway through. The innermost inner core, which geophysicists have taken to calling the IMIC, has its own distinct crystallographic orientation, suggesting it formed under different conditions, or at a different time, or responded to forces that the outer shell of the inner core did not experience in the same way. What this likely means, and here the science shades into inference, into the careful, hedge-everything language that honest researchers use when they are near the edge of what can be confirmed, is that the innermost inner core is a fossil, a record of an earlier chapter in the planet's deep history, locked in crystal alignment the way tree rings lock in the history of wet years and dry ones, the way the grain of ancient rock preserves the direction of long-gone magnetic fields. Something happened long ago in the deepest interior. A change in the direction of growth, perhaps. A shift in the thermal conditions. A different period of the inner core's development before it settled into the pattern it shows in its outer layers. And that earlier period is still there, still legible if you have waves patient enough to read it. A ball within a ball within a ball, and in the very center, the oldest record. Now let us follow the heat outward, because the story of the inner core is not only a story of what is happening inside it, it is equally a story of what it gives to the rest of the planet as it slowly, exquisitely, slowly grows. The inner core is freezing. Right now, as you lie in the dark, the boundary between the inner and outer core, a surface nearly 7,000 kilometers beneath you, where solid iron-nickel meets liquid iron-nickel, is crystallizing one atom at a time, adding the outermost layer of the inner core's vast sphere. The growth rate is about 1 millimeter per year. 1 millimeter. You could cover that distance in a single, slow breath, the movement of your chest rising and falling. But accumulated over 1 million years, that 1 millimeter per year becomes 1 kilometer of new, solid iron added to the inner core's radius. Over 1 billion years, it becomes 1,000 kilometers. The inner core, now roughly 1,220 kilometers in radius, has taken between 500 million and 1.5 billion years to reach this size. Think about what that means, 1 millimeter per year. There is almost certainly nowhere else in the planet where growth happens so slowly, so quietly, so patiently. Mountains rise and erode on timescales of millions of years, which sounds slow, but mountains rise by kilometers in those spans. The inner core adds 1 millimeter. Glaciers advance and retreat. Continents drift across the surface at speeds of a few centimeters per year, measurable in a human lifetime. The inner core grows at perhaps 1/20th of that drift rate. It is the slowest large-scale growth process known in the solid Earth, a construction project that makes the movement of tectonic plates look hurried. And yet this slowness is precisely where its power comes from. When liquid iron crystallizes into solid iron at the inner core boundary, two things happen simultaneously. The first is the release of latent heat. Freezing for water and for iron alike releases energy, the energy that was holding the atoms in their more dispersed liquid arrangement, now surrendered as they lock into the orderly structure of a crystal. At the temperatures and pressures of the inner core boundary, this latent heat is substantial. It flows outward into the liquid outer core as thermal energy, helping to maintain the temperature gradients that drive convection, that slow, churning circulation of liquid metal that generates Earth's magnetic field. The second thing that happens is a chemical expulsion. Pure iron crystallizes more readily than the mixture of iron and lighter elements that makes up the outer core. When iron atoms lock into the solid inner core, the lighter elements, sulfur, oxygen, silicon, possibly some carbon and hydrogen as well, though the exact proportions remain one of geophysics' genuinely open questions, are left behind in the liquid. They are expelled from the freezing front, released back into the outer core as the iron crystallizes around them, and because these light elements are, as their name suggests, lighter than the iron-dominated liquid surrounding them, they rise. They become buoyant. They float upward through the outer core, carrying chemical energy with them, driving a form of convection that works alongside the thermal convection driven by latent heat. Together, these two effects, the thermal energy of freezing and the chemical buoyancy of expelled light elements, are what power the geodynamo. The great convecting ocean of liquid iron-nickel in the outer core circulates because the inner core is freezing at its base. Without that freezing, the convection would weaken. Without convection, the geodynamo would falter. Without the geodynamo, Earth's magnetic field would diminish, perhaps collapse into the kind of weak, wandering, irregular field that Mars now has. And that Mars, without a large, solid inner core to drive its dynamo, apparently lost long ago. The magnetic field is not merely a feature of the planet, it is a shield. It deflects the solar wind when the constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second around the planet, preventing those particles from stripping away the atmosphere and bombarding the surface with radiation. Life on land, life anywhere above the ocean's protective depths, depends on the magnetic field's existence in ways that are easy to take for granted until you consider what planets without it look like. Mars, dry, thin-atmosphered, radiation-blasted Mars, which once had liquid water on its surface, and may once have had a thicker atmosphere and a stronger field, has drifted toward its current state in part because its core cooled too quickly, its dynamo weakened, and its shield thinned. The inner core of the Earth, that quiet, slowly freezing ball of iron crystals, 1 millimeter thicker each year, generating latent heat and buoyant light elements as it grows, is part of what has kept this planet habitable for billions of years. The magnetic field that allows life to exist on land is powered, in part, by the patient growth of that iron sphere. There is a direct, unbroken chain of causation from the crystallization of iron at the inner core boundary to the existence of complex life on the surface above it. The inner core is not an obscure geological detail. It is one of the foundations on which everything above it rests. And here is something that still carries a quiet astonishment, even after all the layers of explanation. The inner core is young, geologically, cosmically young. In a planet 4.5 billion years old, the inner core has existed for somewhere between 500 million and 1.5 billion years. For most of Earth's history, for 3 billion years or perhaps longer, there was no solid inner core. The entire core was liquid, a vast spherical ocean of iron-nickel, circulating and convecting, but without the crystalline heart at its center that exists now. What was the magnetic field like then? This is where the science becomes genuinely uncertain in ways that are honest and worth sitting with. Paleomagnetic records, the frozen magnetic signatures preserved in ancient rocks as they cooled through what's called the Curie point, locking in the direction and intensity of the field at the moment of their formation, suggest that Earth has had a magnetic field for at least 3.5 billion years, possibly longer. So the planet was magnetically shielded long before the inner core existed. The dynamo operated in a fully liquid core for most of Earth's history, but the field may have been weaker or more variable, or at certain points nearly collapsed. There is evidence in paleomagnetic records of periods when the field intensity dropped dramatically before recovering. Andrew Biggin and colleagues in 2015 found evidence in ancient rocks suggesting the magnetic field was unusually weak around 1 billion years ago, possibly near collapse, and then recovered, strengthening around the time that estimates suggest the inner core may have begun to nucleate, to form, as if the birth of the solid inner core re-energized the geodynamo, injected new power into the convecting liquid around it, and pulled the magnetic field back from whatever edge it had approached. The nucleation of the inner core, the moment when, somewhere in the thermal and chemical history of the cooling planet, the first crystals of solid iron formed at the very center of the liquid core and the solid ball began to grow, may have been one of the most consequential events in the history of life on this planet. Not because it was dramatic in any immediate sense, it would have been invisible at the surface, unfelt, unwitnessed by any creature alive then. But it set in motion the long, slow process of core freezing that powers the geodynamo we still rely on. The magnetic shield that protects complex life on land may owe its current vigor, in part, to a phase transition that began quietly in the iron at the center of the Earth, perhaps 1 billion years ago, perhaps less. And that freezing is still happening. Right now, 1 millimeter per year at the boundary between solid and liquid iron, 6,500 kilometers beneath you, at a temperature of roughly 5,300 degrees Celsius and a pressure of more than 300 gigapascals. In geological time, the inner core is still a young thing, still growing, still in the middle of a process that will continue for billions of years to come. Does any of this change from moment to moment in ways we can feel? Does the quiet rocking of the inner core's differential rotation, the slow back and forth that Yang and Song measured in 2023, the possible oscillation that Vidale and Wang found evidence for in 2022, the backtracking around 2010 that Vidale's team reported in 2024, Does any of that reach the surface and change something in our daily world? The answer is almost certainly yes, in the tiniest, most imperceptible of ways. The length of a day on Earth, 24 hours, or more precisely, a certain number of atomic clock seconds that we measure with exquisite precision and continuously monitor, is not perfectly stable. It varies by milliseconds over the course of decades, speeding up and slowing down in a pattern that has been tracked for a long time by geodesists, the scientists who measure the shape and rotation of the planet. Some of this variation comes from the atmosphere. Seasonal changes in the distribution of air mass across the globe shift the planet's moment of inertia slightly, the way a spinning ice skater changes speed by pulling in or extending their arms. Some comes from the oceans, some from glaciers, and some possibly from the deep interior, from the coupling between the inner core and the mantle above it. If the inner core is indeed oscillating on a roughly 70-year cycle, creeping slightly ahead of the mantle, then falling slightly behind, then creeping ahead again. And if this oscillation is coupled to the mantle through gravitational and electromagnetic forces, then the inner core's back-and-forth rhythm may be subtly influencing the planet's overall rotation, adding or subtracting milliseconds from the length of the day over decades-long cycles. Yang and Song, in their 2023 paper, noted this possible connection. The correlation is suggestive, though not yet definitively proven. It is another thread in the web of interactions between the deep interior and the surface that scientists are still working to trace. But even if the correlation is real, even if the inner core's gentle oscillation does reach upward through 6,500 kilometers of rock and metal to touch the length of the day, the effect is measured in milliseconds, not seconds, not minutes, milliseconds, fractions of a second spread across decades, detectable only by atomic clocks and geodetic instruments of extraordinary sensitivity. No clock you own can measure it. No experience you have will ever feel it. It is real, and it is vanishingly small, and it is one more reminder of how the deep interior of the planet communicates with the surface only in the most subtle possible ways. A ball that is 1% of Earth's mass by weight, buried at the center, exerts an influence on the magnetic shield that protects all life, on the length of the day as measured by atomic clocks, on the subtle architecture of the planet's seismic wave field. 1% of the mass. And yet, the magnetic field, the length of the day, the innermost crystal structure of a planet. The disproportion between what the inner core is in terms of mass and what it does in terms of consequence is remarkable. There is a kind of geometry to this realization that rewards sitting with in the dark. The inner core is small as planetary features go. While its radius is roughly 1/5 of the Earth's total radius, its volume a much smaller fraction still. Set it beside the whole planet and it looks like the seed inside a fruit. And yet the entire planet's magnetic personality, the shield that separates life from the solar wind, depends in part on what happens at that seed's surface, at the slow crystallization front, where liquid iron becomes solid iron, 1 millimeter per year. The planet is, in some sense, organized around a process happening in a space no larger than the distance between your city and the one perhaps 1,200 kilometers away. Everything above, the liquid metal ocean of the outer core, the dense rocky mantle, the thin crust, the oceans, the atmosphere, the biosphere, is in some way downstream from what happens at the inner core boundary. We will never go there to see it. The Kola Superdeep Borehole, drilled by Soviet engineers over nearly 2 decades, reaching a final depth of 12.25 kilometers in 1989 before heat and pressure made further progress impossible, penetrated less than 0.2% of the distance to the center. The drill bit that stopped at 12 kilometers was still, geologically speaking, barely below the surface. The inner core is more than 6,000 kilometers further down. No material we can construct, no technology we can currently conceive would survive the 330 to 360 gigapascals of pressure and the 5,000-degree temperatures of the deep interior. The center of the Earth is, and likely will remain for a very long time, the most inaccessible place on this planet. And yet, and this is the thing worth returning to at the end of a long journey through the layers, yet we know it. We know it because the planet tells us, in the language of seismic waves, in the timing of earthquake signals, crossing and recrossing through its interior, in the subtle differences between the wave that traveled from the South Sandwich Islands to Alaska in 1967 and the nearly identical wave that traveled the same path in 1995, carrying in that tiny difference the fingerprint of a slowly rotating iron sphere that had moved just enough in those intervening decades to shift the path it presented to the sound passing through it. We know it because Inga Lehmann, working alone in 1936 with paper records and a steady, meticulous mind, looked at the shadows in the seismic data, the places where P waves arrived when they should not have been able to, and inferred that only a solid sphere nested inside the liquid could bend them that way. Her paper was titled simply P, one of the most compressed, understated titles in the history of science, for one of its most remarkable acts of inference. She was reading the interior of the planet from its surface, the way a doctor reads the interior of the body from the outside, the way an astronomer reads the interior of a star from the light arriving at a telescope. The Earth cannot be opened. So she listened to it instead. We know it because Xiaodong Song and Paul Richards looked at decades of seismic records in 1996 and noticed the inner core spinning slightly ahead of the planet above, a discovery that launched a generation of research and debate. Because Yang and Song in 2023 looked at even longer baselines and saw the rotation slow, approach zero relative to the mantle, and possibly tip into a gentle reverse, not a catastrophe, not a cause for alarm, but a quiet oscillation in a system of extraordinary complexity that has probably been rocking back and forth for longer than our records can reach. Because John Vidale and his collaborators found independent traces of the same oscillation in seismic records from underground nuclear tests in the late 1960s and early 1970s, sounds made by human instruments rather than earthquakes, still carrying the inner core's signature in their timing. Because Thanh-Son Pham and Hrvoje Tkalcic spent years collecting the faint, 5-bounce echoes of earthquakes that had crossed the planet's full diameter 5 times, those whispers of waves, still coherent enough after 2 hours of travel and 5 traversals of the deep interior to tell them that the very center was crystallographically different from the layer surrounding it. This is what knowledge of the deep Earth actually looks like. Not a drill, not a camera, not a sample. Inference, pattern recognition, decades of data from seismograph stations distributed across the planet, maintained by scientists in many countries, quietly recording the planet's vibrations the way a doctor's stethoscope quietly listens to the chest. The picture built up slowly, one measurement at a time, one earthquake at a time, over more than a century, from Oldham in 1906 finding the core atoll, to Gutenberg in 1913 locating the core mantle boundary, to Lehmann in 1936 finding the solid inner sphere, to the decades of refinement since that have mapped its anisotropy, its rotation, its subtle substructure, and now its possible oscillation. And the picture, after all that work, is this. At the center of the Earth, there is a ball of iron-nickel crystals, roughly 1,220 kilometers in radius, slightly larger than the dwarf planet Pluto, which takes more than 5 Earth years to complete a single orbit of the Sun, and which we reached for the first time only in 2015, a journey of 9.5 years across 4.5 billion kilometers. That is how big the inner core is, a Pluto buried beneath your feet. That iron ball is hotter than the surface of the Sun, not the Sun's interior, the surface, the visible layer called the photosphere, where sunlight originates at roughly 5,500 degrees Celsius. The inner core's temperature is in the same range, perhaps somewhat higher by some estimates, and yet it is solid, not because it has cooled below iron's melting point, but because pressure at 330 to 360 gigapascals, more than 3 million, times the pressure of the air around you right now, raises the melting point of iron above the local temperature. The iron at the center of the Earth would be liquid at any pressure we can easily imagine. At the pressure of the deep interior, it freezes. That solid iron ball is spinning. It has been spinning since the planet formed, and it will keep spinning long after every trace of our civilization has dissolved back into the geology. For most of that long time, it has probably been spinning at roughly the same rate as the planet above it, give or take a tiny fraction of a degree, sometimes slightly ahead, sometimes now apparently slightly behind, back and forth over a cycle of perhaps 70 years, coupled to the rest of the planet through the liquid metal ocean surrounding it. An oscillation so gentle that it changes nothing perceptible at the surface, nothing that any human being will ever directly feel, measurable only by the accumulated record of seismic waves and atomic clocks and the patient work of scientists who have made listening to the planet their life's work. Inside that spinning iron ball, there is another, 600 kilometers in radius, with its crystals pointing a different way, a record of something that happened deep in the planet's past, an ancient chapter preserved in crystal alignment, the way amber preserves what was alive inside it. A ball within a ball within a ball. And we found it by counting the bounces of earthquake echoes crossing the planet 5 times. Right now, as the night settles and quiets, all of this is happening. The inner core is adding its millimeter of new iron, one crystal at a time, releasing latent heat and buoyant light elements into the liquid outer core above it, feeding the convection that drives the geodynamo, sustaining the magnetic field that deflects the solar wind and keeps the sky above you from being slowly stripped away. The liquid outer core is churning, its currents of iron-nickel completing circuits that function like the windings of an enormous generator, maintaining the invisible field that extends tens of thousands of kilometers out into space. The mantle is creeping too slowly to feel over a human lifetime, but faster, in geological terms, than the inner core grows. The crust is drifting. The planet is doing what it has always done, all the way down to its center, where a quiet iron heart turns in the dark. You cannot hear it. There is no medium through which that sound, if it existed, could reach you. And in any case, the energy is all seismic, frequencies far below the range of human hearing, vibrations of rock and metal across thousands of kilometers that only instruments built for the purpose can detect. But if you think of it as a sound, a deep and very slow note, somewhere below any pitch a human ear could register, it has been playing since before there were ears to hear it, and it will continue playing long after any record of our existence has been absorbed back into the earth. The inner core does not know it has been discovered. It does not know that in 2023, 2 researchers at Peking University analyzed decades of earthquake records and noticed that its differential rotation had slowed. It does not know that a team in Canberra spent years counting the bounces of seismic waves to find the different crystals at its center. It turns and freezes and powers the field above it and keeps its ancient crystallographic record at its heart, entirely indifferent to the science being done in its name. But we know. And there is something genuinely moving about that, about the gap between the inaccessibility of the thing and the precision with which we have come to understand it. A ball we will never touch, never see, never sample, never send a probe toward. farther from us than any spacecraft has ever traveled, measured not in kilometers of space, but in kilometers of crushing, incandescent rock and metal. And yet, we know its radius, its temperature, its crystal orientation, the direction its crystals point at its very center, the rate at which it grows, the gentle rhythm of its rotation relative to the ground above it, the age at which it formed, the way its birth may have re-energized the magnetic field and contributed in ways we are still tracing to the conditions that allow life to exist on its surface. All of this from the echoes of earthquakes, all of it from listening. There is a particular kind of peace in this when you sit with it long enough. The universe is full of things we cannot reach or see or touch. The interior of stars, the surfaces of exoplanets, the conditions a fraction of a second after the universe began. And yet knowledge finds its way in anyway, carried by light and sound and gravity, decoded by patient minds with careful instruments, built up over generations of slow, cumulative work. The inner core of the Earth is one more example of this, of how knowledge does not require contact, does not require direct experience, but can be built from inference and patience and the willingness to listen very carefully to what the world is saying. The planet has been talking all along. The seismic waves have been crossing and recrossing through its interior for as long as earthquakes have existed, which is to say, for as long as the planet has had a solid crust and a churning interior, billions of years before there were instruments to detect them. All those signals carrying the fingerprints of every layer they passed through, arriving at surfaces where nothing was there to read them. Then slowly, humans arrived. Built instruments, learned to read the signals, and began, layer by layer, to construct a picture of a world that cannot be seen. The iron ball at Earth's center did not change direction in any way that should alarm you. It shifted its tiny differential rotation, the small lead it had been running over the mantle above it, slowing that lead across decades, reaching something close to zero around the year 2009 and perhaps tipping into a gentle lag, part of a back and forth that has probably been going on for human generations, maybe longer, a 70-year breath in a system that has been breathing for billions of years. The planet does not notice. You do not notice. The magnetic field does not waver. The length of the day changes by milliseconds that no clock you own can measure. Everything above the core continues exactly as it has, while beneath it all, the quiet iron heart makes its slow adjustments and keeps turning. This is what is actually happening beneath the headlines and the alarm. Not a catastrophe, not a collapse. A gentle oscillation in a system of astonishing complexity, discovered by decades of patient listening, confirmed by independent teams using different methods and different data, debated in careful scientific language that acknowledges what is known and what remains uncertain, and understood, the extent that it is understood, as one more layer of the deep planet's character being slowly, patiently mapped. The inner core will keep freezing, 1 millimeter per year for billions of years to come. The outer core will keep churning. The geodynamo will keep running. The magnetic field will keep deflecting the solar wind. And somewhere in the crystallographic record of the innermost inner core, that 600-kilometer sphere at the very center, with its crystals pointing a different way, the memory of an earlier chapter in the planet's history will keep waiting, patient and undisturbed, for future instruments and future scientists to read it more clearly. If you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I do read them. There is something quietly wonderful about knowing that people in different places, different time zones, different skies, are all resting above the same iron heart, the same slow freezing, the same ancient turning in the dark. There are more stories here of the same slow and careful kind, waiting for whenever you want them. But for now, you have traveled far enough. Down through the crust and the mantle, through the liquid ocean of the outer core, through the crystalline surface of the inner core, and all the way to its hidden center. You have followed the echoes of earthquakes across the planet's diameter 5 times over. You have understood, as well as any of us can, what is happening 6,500 kilometers below your bed. You have done enough for tonight. Put down whatever remains of the day. The iron heart is turning quietly beneath you, as it has been turning for 500 million years, as it will turn long after tonight is forgotten. It does not need your attention to continue. It will freeze its millimeter, power its field, and keep its ancient record whether you are awake or asleep. History will still be here in the morning. For now, rest.